So in the previous class, I have already discussed the questions numbering from 1 to 13. I have discussed the solutions and answers for the questions from 1 to 13 in my previous class in the Feynman Newton's laws. So now I am going to discuss the solutions of the questions numbering from 14 onwards in this class. In case there may be some exception students who may not have any doubts in the first 20 questions or 22 questions, in that case they can skip this class also. They can go to the next class directly. So come on, look at the question number 14, which I already shown you earlier. Again, I am showing the same question. I am going to discuss the solution of this question. Two blocks of masses 2 kg and 1 kg are in contact with each other on a frictionless table. When a horizontal force of 3 Newton is applied to the block of mass 2 kg, the value of the force of contact between the two blocks is. So, I would like to draw the free body diagram for each block here. So the two blocks are placed in contact. Based on the description, you can try to draw the figure. Showing the situation in the problem. I call the mass of the first block are denoted by M1. Mass of second block are denoted by M2. Of course, here M1 is 2 kg and M2 is 1 kg. The horizontal force applied on the first block of mass M1 equal to 2 kg. I denote the magnitude of the force applied on the first block by F. In the past, I have discussed similar question before assignment in bodies in contact with a small difference. Here, pushing force applied in the horizontal direction. In the problem I have discussed in the past, pushing force applied from angle to the horizontal. So, during the motion, the mass M1 pushes M2 towards right. So, the mass M1 exerts a force on M2 towards right. So, I draw a separate figure showing the contact forces between the blocks. So, during the motion, let us suppose both the blocks move towards right under the action of the force applied. So, during the motion, the first block of mass M1 pushes the second block of mass M2 towards right. So, the first block of mass M1 exerts a force on M2 towards right. So, the force on M2 by M1 acts towards right, which I have denoted by vector form F bar to 1. So, during the motion, the mass M1 pushes the mass M2 towards right. So, the mass M1 exerts a force on M2 towards right. According to Newton's third law, to every reaction there is always equal and opposite reaction. Here action is the force on M2 by M1, which acts towards right. So reaction will be directed towards left. So reaction will be the force on M1 by M2, which may be denoted by F bar 1, 2. But this action-reaction forces are equal in magnitude but are oppositely directed. So if you write in vector form, F bar 1, 2 is negative of F bar 2, 1. But if you consider the modulus, the magnitude of F bar 1, 2 is same as magnitude of F bar 2, 1. Let F dash denote the magnitude of the contact force between the two blocks. That means magnitude of force on M2 by M1 is F dash. The modulus or magnitude of reaction force on M1 by M2 is also equal to F dash. I draw a separate three-body diagram for each block. The forces which act on M1 must be indicated as three-body diagram for M1. The forces which act on M2 must be shown in the free body diagram for the mass M2. FBD means short form for free body diagram. So here action is the force. If you consider the contact force between the two blocks, action is the force on M2. So it should be indicated in the free body diagram for M2, which acts towards right with magnitude F dash. This reaction is the force on M1. So it should be indicated in the free body diagram for M1, which also has same magnitude F dash. This F is the horizontal force. That kept left denote the magnitude of the horizontal force applied on the first block of mass M1 equal to 2 kg. So which should be shown in the free body diagram for M1. The forces which act on M1 must be indicated in the free body diagram for M1. In the vertical direction, the weight of each block acts downwards. So weight of the first block has magnitude M1G, which acts vertically downwards, which is the gravitational force on M1 by the earth. Let N1 denote the magnitude of the normal reaction force on M1 by the surface of the table on which the blocks are resting. It acts perpendicular to surface and directed away from surface of the table. Similarly, for the mass M2, its weight M2G acts downwards. M2G is the magnitude of the gravitational force on M2 by the earth. The normal reaction force on M2 by the surface of the table acts vertical upwards, perpendicular to surface of table in contact and directed away from surface of table in contact. So N2 represents the magnitude of normal reaction force on M2 by the table. So here both the blocks are moving in the horizontal direction towards right with the same acceleration. So I choose the horizontal direction, which is the direction of the motion of each block as x-axis, positive direction of x-axis, and vertical upward direction of the y-axis. So the blocks do not have any acceleration in the vertical direction. The blocks have no motion in the vertical direction. So y component resultant force on M1 is 0. Y component resultant force on M2 will also be 0. That means weight M1G of the first block is balanced by normal reaction N1. The weight M2G of second block is balanced by the normal reaction N2. So resultant force on M1 will be equal to resultant of the forces acting in the horizontal direction. So magnitude of the resultant force on the mass M1 is equal to resultant of the forces in the horizontal direction. Or we write Fx. Here F is the magnitude of the horizontal. Look at the free body diagram for M1. F is the magnitude of the horizontal force applied on M1, which acts towards right in the direction of its motion. F dash is the magnitude of the reaction force on M1 by M2, which acts towards left, opposite to the motion. So magnitude of the resultant force on M1 towards right will be equal to F minus F dash. From Newton's second law, the magnitude of the resultant of all the force acting on M1 will be equal to product of the mass M1 and magnitude of its acceleration. Let small a denote magnitude of acceleration of each block. Then look at the free body diagram for M2. So resultant force on M2 will also be equal to Fx, means resultant of forces in the horizontal direction. The only force which acts on M2 in the horizontal direction is equal to F dash, which represents the magnitude of the force on M2 by M1, which acts towards right. From Newton's second law, resultant of all the forces on M2 will be equal to product of its mass and acceleration. So acceleration is same for both the blocks here. So if you add the equations 1 and 2, so F minus F dash plus F dash equal to M1A plus M2A. Or you can write F equal to, so when the two blocks move towards right with the same acceleration on a smooth horizontal surface, then we can write F equal to M1 plus M2A. You can substitute this value of A from in the second equation. You can substitute A equal to F by M1 plus M2 from in the second equation. So from second equation, F dash, that is the magnitude of the contact force between the two blocks, will is denoted by F dash is equal to M2A. You can substitute A equal to F by M1 plus M2. So I have solved the problem first in letter notation. Now come on, those who want to copy the solution of the problem, they can copy down the solution of the problem. Can substitute the values. M2 is given to 1 kg. M1 is given to be 2 kg. F is given to be 3 Newton. So you get the answer as 2 Newton. You can simplify it yourself. So magnitude of the contact force between the two blocks is 2 Newtons. I'm sorry, not 2 Newtons. Magnitude of the contact force between the two blocks, you will get it as 1 Newton. So answer is 1 Newton. Answer is 1 Newton. So in case you need more time to copy the solution of the problem, you can take a pause and take your time. See the 15th question. A body of mass capital M be dropped from a height h on a sand floor. The body penetrates a distance x into the sand. The average resistance offered by the sand to the body is. I have already shown you this question earlier on the screen. So I am going to discuss this question now. So if a body, that means here the body first falls freely under gravity from height h. As we discussed earlier in kinematics, the body falls freely under gravity from a height h above the floor. then magnitude of its velocity just before it strikes the floor will be equal to root of 2gh. The magnitude of its velocity just before it strikes the floor will be root of 2gh. That means the body begins to move in the sand starting with a velocity of root 2gh. So let us suppose the body first moves from a position A to the position B before it enters into sand. Let us suppose the body penetrates from position B to the position C in sand. So velocity becomes 0 at the position C. So from distance from A to B equal to h, the vertical distance from B to C equal to x. So the velocity at B will be equal to root 2gh. Starts falling freely under gravity starting from the point A. Velocity is 0. So for motion from A to B, it moves under influence of gravity. So for motion from A to B, it moves under influence of gravity like a freely falling body. So using the formula v square minus square equal to as. So square of the velocity at B minus initial velocity is 0 is equal to acceleration equal to g. So well, square of the velocity at B is 2gh. That can be taken as initial velocity for motion from B to C in sand. So for motion from B to C in sand, the initial velocity at B is equal to root 2gh. Final velocity at C becomes 0 after it travels a distance s equal to x. To find the force, you have to calculate the acceleration. So we use the equation in kinematics in terms of these 4 letters U, V, A, F. So can use the equation V square minus square equal to AS for motion inside the sand. Final velocity is 0 at C. Initial velocity at B is root 2gh. S equal to x. So you get here the acceleration for motion inside the sand minus gh by x. So we have taken here a downward direction as positive direction. We have given positive sign for velocity and displacement in the downward direction. So we got negative sign for acceleration, means acceleration is opposite to the displacement in sand, means acceleration is directly opposite to the motion. That means the retarding force exerted on the body by the sand will be directed upwards. So during the motion in sand, 2 forces act on the body. One is its weight mg, which acts vertically downwards, which is the gravitational force of the body by the earth. Let Kepler denote the magnitude of the retarding force or opposing force exerted by the sand, which we sometimes call resistance. So this is the free body diagram for the body during motion inside the sand. There are 2 forces in opposite directions. We are choosing the downward direction. Direction of the motion is positive direction. So therefore, resultant force in the direction of the motion during the motion in the sand, you can write mg minus r. From Newton's second law, that can be written as product of its mass and acceleration. So from this equation, you get mg minus ma equal to r. So you can write r equal to m into g minus a. You can substitute here a equal to minus gh by x. So finally get magnitude of the average retarding force or resistance force exerted by the sand on the body is equal to, given by r equal to mg into 1 plus h by x. So that's the answer. So answer is mg into 1 plus h by x. Come on, those who want to copy the solution of the problem, they can copy down the solution of the problem. This problem was originally given one of the previous medical entrance exam in EAMCET. In case you need more time to copy the solution of the problem, you can take a pause and take your own time. Next, I am going to discuss the question number 16. See the next question, question number 16. The mass of a balloon and its contents is capital M, is descending with an acceleration A. By how much the mass should be decreased, keeping the volume constant, so that the balloon starts ascending with the same magnitude of acceleration. So here I draw the free body diagram for the body. The concept here, you have to assume that volume remains constant in both the cases. Therefore, that means the volume of the balloon remains constant. So therefore, you can assume that the balloon displays the same quantity of air in both the cases. Therefore, the upward force of buoyancy or upthrust on the balloon can be assumed to be the same in both the cases. From the Archimedes principle, of course, we'll discuss it in fluid mechanics again about the Archimedes principle. But you must you might have heard the name Archimedes in the school. So the magnitude of the force of buoyancy or upthrust on the balloon will be equal to the magnitude of the weight of air displaced. Because the volume of the balloon is constant or same in both the cases, so you can assume that same quantity of air is displaced by the balloon. Therefore, magnitude of the force of buoyancy on the balloon can be assumed to be the same in both the cases, or upthrust. Let us suppose R is the magnitude of the force of buoyancy or upthrust on the balloon, which is same in both the cases. So two forces act on the balloon. In the first case, weight mg acts vertically downwards, which is the gravitational force on the balloon by the earth. Secondly, the upward force of buoyancy or upthrust acts upwards. So in the first case, the balloon is moving vertically downwards with an acceleration of magnitude small a. So whatever calculation I am doing for question number 16, same calculation also applies for next question, question number 17. That means I am going to use the result of this question directly for next question. So here I choose the downward direction of the motion as positive direction in the first case. So magnitude of the resultant force of the balloon in the downward direction is equal to mg minus r. From Newton's second law, this will be equal to product of mass of the balloon and magnitude of its acceleration. So we can write as mA. In the second case, you are asked to find the mass that should be removed or detached from the balloon so that it begins to move upward with the same magnitude of acceleration. So in the second case, let us suppose the mass detached from the balloon mass removed from the balloon by m dash. I denote the mass detached or removed from the balloon by m dash. So now remaining mass of the balloon with contents in the second case will be m minus m dash. So mass of the balloon with contents second case will be m minus m dash. So weight of the balloon in the second case you can write m minus m dash into g. But magnitude of the force of buoyancy or thrust of the balloon remains same in both the cases, which is denoted by Kepler. So in the second case, it is moving, it has to move upwards. You are asked to find the mass m dash which should be removed from the balloon so that it starts moving upwards with same magnitude of acceleration. I write m dash again, second time for more clarity. The same magnitude of acceleration A. Second case, the motion is upward, so we choose the upward direction as positive. So magnitude of the resultant for the balloon in the second case will be r minus m dash into g in the upward direction. This resultant force acts in the upward direction. So from Newton's second law, magnitude of the resultant force on the balloon in the upward direction second case equal to product of mass and magnitude of its acceleration second case. Mass of system in second case is equal to m minus m dash. Magnitude of acceleration is again A. So you have to find m dash in terms of m, a and g. For that you have to eliminate r from the two equations. So you can add the equations 1 and 2. So mg minus r plus r minus m dash into g is equal to ma plus m minus m dash into a. Can simplify it to yourself. Come on. Try to do the simplification yourself. Those who want to copy the solution of the problem, come on, they can start writing the solution. So minus r plus r get cancelled here on the left side. So you can collect the terms containing m dash to the left hand side. Left side again mg gets cancelled. Right side you get 2ma. So you get m dash equal to 2ma by g plus a. That's the answer. So this result I am going to directly use for solving the next problem. That means in general, if total mass of the balloon along with contents is denoted by capital M in the first case, and if the balloon is moving vertically downwards with an acceleration of magnitude A in the first case, then mass that should be removed from the balloon so that it begins to move upwards with same magnitude of acceleration is given by m dash equal to ma by g plus a. That's the answer. In case you need more time to copy the solution of the problem, you can take a pause and copy the solution of the problem. See the question number 17. Can read out the question. It is same model as the previous problem. Here I am going to use the result of the previous problem directly to solve this problem. The mass m of the balloon in the first case is given to be 1.5 kg. The magnitude of acceleration is same in both the cases, that is equal to g by 2. So the mass m dash, which should be detached from the balloon so that it begins to move upwards, the same magnitude of acceleration is given by m dash equal to ma by g plus a. That is 2 into 1.5 kg is g by 2. So g plus g by 2. So if you simplify this, you get m dash equal to 1 kg. That's the answer. So this problem was originally given one of the previous EAMCET examinations. I think it was given in 1999 EAMCET in engineering with the same numericals. So next I am going to discuss the question number 18. So the question number 18, a body of mass 5 kg starts from the origin with an initial velocity u bar equal to 30 I bar plus 40 J bar meter per second. If a constant force F bar equal to 6 I bar minus 5 J bar Newton acts on the body, the time in which the y component of velocity becomes 0 is. So here it is a problem with two-dimensional motion with constant acceleration. So you can use the equations of one-dimensional motion with uniform acceleration separately for motion parallel to x-axis and separately for motion parallel to y-axis. For a body moving in the xy plane, the initial velocity in vector form, you can write u bar equal to ux I cap plus uy j cap. So by comparing the given equation with this equation, you can observe that x component of initial velocity is 30 meter per second. The y component of initial velocity is 40 meter per second. And for the constant force acting on the body in the xy plane can be written as I cap into fx plus j cap into fy. Here y component of the force you can write. We are considering the motion parallel to y-axis here. Fy is minus 5 newtons. Fx is 6 newtons. The value of fx and ux are not required to answer the question because you are asked to find the time after which y component velocity becomes 0. For which you have to find the acceleration in the y direction. Y component of acceleration you can write y component of force by mass of the body. The y component of the force equal to minus 5 Newton. Mass is 5 kg. So y component of the acceleration will be minus 1 meter per second square. So you can use the equation v equal to u plus at for motion parallel to y-axis. Y component of final velocity of time t, you can write y component of initial velocity plus y component acceleration to time. That is Vy equal to Uy plus Ay. So you have to find the time after which Vy becomes 0. So you can substitute Vy equal to 0 on the left side to solve the problem. And Uy is 40 meters per second. Acceleration Ay is minus 1 meter per second square. And you have to find time t after which y component velocity becomes 0. So you get the answer as 40 seconds. So in case you want to copy the solution of the problem, come on, copy down the solution of the problem. This problem was originally given in the EAMCET examination in the medical entrance. I think it was given in 2000, EAMCET medical entrance. Next time, in case you need more time to copy the solution, you can take a pause and take more time. See the question number 19. Circular plate of mass 10 kg is to be kept floating in midair by firing bullets each of mass 10 gram with a velocity of 50 meters per second. The number of bullets that must be fired per second if the bullets after striking the plate fall freely is. So I denote the mass of each bullet by small letter m, that is 10 gram. So we can write as 10 into 10 power minus 3 kg or 10 power minus 2 kg. The mass of the circular plate I denoted by capital letter M, which is equal to 10 kg. So the initial velocity of each bullet before it strikes the plate. So it understood that the bullets strike the plate from below. That U bar denote the velocity of the bullet in vector form just before the collision with the circular plate. I have shown the thickness of the plate in the figure, or diameter of cross section of the plate here. So it is given that the bullets fall freely after striking the plate. That means the velocity of each bullet just after striking the plate can be taken as 0. I mean, the velocity of each bullet just after impact with the plate can be taken as 0, because it is given that the bullets fall freely. So from force, so the force on plate by the bullets act in the upward direction. So reaction force on bullets by the plate acts downwards. So force on bullets by plate is equal to rate of change of linear moment of the bullets. So change in moment of one of the bullets is equal to m into v bar minus u bar, where v bar is the velocity of each bullet just after impact with the plate. U bar is the velocity of the bullet just before impact with the plate. Let n denote the number of bullets that strike the plate per second. So change in momentum of bullets per second, or rate of change of linear moment of the bullets, can be the change in momentum of one bullet due to impact with the plate into number of bullets that strike the plate per second. Here V bar is 0 bar, because after impact with the plate each bullet falls freely. That means velocity of each bullet just after the impact with the plate can be taken as 0. So initial velocity of each bullet in vector form, I choose the vertical upward direction, suppose as positive direction of x-axis, or you can take y-axis, any one of the way. So U bar can be written as 50 I cap meter per second in vector form. So m into v bar is 0, u bar you can write. So that will be into small n. So the 4 minus mu bar n. From Newton's third law, action and reaction force are always same in magnitude, but opposite in direction. So the force on bullets by the plate is minus mu bar n. Negative sign implies that the force on bullets by the plate acts downwards. So from Newton's third law, force on plate by bullets must be equal and opposite. Will be equal in magnitude but opposite in direction to the force on bullet by plate. So that you can write mu bar n. That means it acts upwards. I denote this force by F bar. To draw a separate free body diagram for the plate, in the free body diagram for the plate, you must show only the forces acting on the plate. So two forces act on the plate here. One is its weight mg, capital M into small g, which is a gravitational force on the plate by that. Second is the force on plate by the bullet, which acts upwards. For the plate to remain stationary in mid-air, to balance the weight of the plate, this is upward, the magnitude of the force upward direction. I mean the magnitude of force exerted on the plate by the bullets must be equal to the magnitude of weight of the plate. So this F is equal to mun in magnitude. It should balance the weight mg of the plate. So capital F must be equal to mg in magnitude. So you can write small m into small u into small n is equal to capital M into small g. So small n equal to capital mg by small m into u. So those who want to copy the solution of the problem, please copy down the solution of the problem. You can substitute and simplify it. Capital M is 10 kg. G, I told you to take 9.8 meter per second square for this problem. Small m is the mass of each bullet, that is 10 power minus 2 kg. U is the magnitude of initial velocity, that is 50 meter per second. So you get n equal to 196 per second. So number of bullets striking the plate per second has to be 196. So answer is 196. Those who are copying the solution of the problem, come on, copy down the solution of the problem. In case you need more time to copy the solution of the problem, you can take a pause and take your time. I am going to discuss the next question, that is question number 20. Look at the question number 20. A man is standing on a weighing machine placed in a lift. Then stationary, his weight is recorded as 40 kg. That means the true weight mg, when the lift is stationary, observed weight is same as true weight, 40 kg weight. Or 400 newtons. Or you can take the mass of the man as 40 kg in calculations. So when the lift is moving upwards with an acceleration of 2 meters per second square, as explained earlier, for a body inside the lift, for a body resting on the floor of the lift, two forces will be acting in opposite direction. One is its weight mg, which acts vertically downwards. Second one is the normal reaction force, which acts upwards. Here N is the magnitude of normal reaction force which acts upwards. So if the lift is moving upwards with acceleration of magnitude denoted by U naught, the net force on the body will be directed upwards. Resultant force is upwards. So we choose the upward direction as positive direction. So magnitude of the resultant force of the body is equal to N minus mg. From Newton's second law, that is equal to product of mass and magnitude of acceleration. So magnitude of the normal reaction force on the body by the floor of the lift is equal to given by m into g plus a naught. Here m is 40 kg, g is 10 meter per second square, a naught is equal to 2 meter per second square. So you get magnitude of the normal reaction force on the body by the floor of the lift will be 480 newtons. You can take 1 kg weight equal to 10 newtons. If g is given at 10 meter per second square, 1 kg weight you can write 10 newtons. So this can be written as 48 kg weight. The apparent weight of the body is same as the magnitude of the normal reaction force on the body by the floor of the lift. So the apparent weight of the body will be 48 kg weight. So in my next class, I am going to continue the solutions of the Feynman and Newton's laws in my next class, starting from 21 onwards. So far, I have completed the discussion of the questions from 1 to 20. Those who want to copy the solution of the problem, they can take a pause and copy the solution of the problem.